Hello everybody, this is Sean McVeigh, National Training Coordinator for the Soil Science Division and host for today's webinar, The Role of Soils in Characterizing the Hydrology of California. This webinar is being recorded and all participants join the webinar in listen-only mode. You receive the webinar audio through the device's speakers. There's no telephone dial-in. If you're having audio difficulties, please check the various ways your computer speakers may be muted or have their volume set low, including the speaker adjustments available in the Adobe Connect interface. You can maximize your webinar experience in Adobe Connect by shutting down VPN and other programs that might compete for bandwidth. This includes email and Microsoft Outlook and instant messaging and Link, now known as Skype for Business. Please take a look at the webinar room layout. I have a content pod, the feature presentation window. I have a Q&A pod and a chat pod. You can enlarge the feature presentation window on your own machine by using the 4-arrow icon in the upper right corner of that featured presentation pod. To submit a comment or question for me or our presenter, use the Q&A pod and type in your question. I'll handle technical difficulties the best I can while hosting the webinar and interact with our presenter to answer your questions during the verbal Q&A periods. I want to thank Maxine Levin, National Leader for Soil Interpretations, for being here to support our webinar and introduce our presenter. Maxine, I'm going to turn the webinar over to you so you can introduce the topic and our presenters.
Okay, well thank you so much, Sean. The title, of course, is The Role of Soils in Characterizing the Hydrology of California, but I want to emphasize that for those of you that aren't from California, a lot of the work that Alan and Lori Flint have been doing over the years with the U.S. Geological Survey and the California Water Science Center is applicable to many, many parts of the country, particularly this watershed basin characterization model that they're going to, I hope, present as part of their work. I originally heard them speak at a CGIS meeting in California this last year, and I immediately saw the connection between soils and the work that they were doing, and I really felt that if nothing else for my staff, that I wanted them to have this presentation and to hear what Alan and Lori Flint have been working on. In addition, you know, we had a very quick, we had a similar webinar earlier this month, last week, with Dr. Lisa Michelli with the Pepperwood Foundation in California. And she also had been using this model along with her other climate change and climate adaptation work that her foundation is doing. And so we sort of went backwards here in that this is the foundational work, and the work that they did last week was the application. So I don't want to say too much more. I'm not sure who's going to start because I think they're a tag team. So Alan, Lori, you take it away.
Okay. Yeah, this is quite fun for us to talk about what we're doing and where soils plays a role in here. As a little bit of background, Lori and I got our master's in forest soils from Oregon State, and we both have PhDs in soil physics, so we're both soil scientists. We went to work for the U.S. Geological Survey in Nevada as hydrologists, looking at Yucca Mountain as a nuclear waste repository. And we were assigned the task of studying the surface soils to calculate infiltration rates and shallow infiltration processes so we better understand how recharge occurs to know whether Yucca Mountain was suitable for nuclear waste or not. If there was too much recharge, it would not be suitable as a natural barrier system. And unfortunately, there's a lot of recharge there because they're shallow soils. So we learned a lot about soil science and how soils play a role in recharge in the desert Southwest, and have moved that since to California. So I'm going to go through some slides and give you an introduction to our modeling work and our ways of estimating recharge, which is what we started this work about. Now, recharge is really difficult to get accurately, and it turns out that hydrologic modeling makes recharge the error term. A lot of the big regional models that are around just simply calculate runoff, measure stream gauges, and whatever's left over seems to go into that term. We're finding water balance modeling can improve the estimates and calibration if we can do all of the hydrologic components rather than have one as an error term. And that's what we have set out to do, and we will go through that with you. So the outline of this talk is going to be what we use as a water balance, the conceptualizing a simple water balance model that describes the hydrologic process along large regions, but we do it at a very fine scale. Each of our grid cells is about 270 meters, so about 18 acres. We're going to look at potential evapotranspiration, how we parameterize snow, what the soil properties are that we need, which is a critical part of the work, the vegetation seasonality of actual evapotranspiration, and then groundwater flow modeling. That's another component. And we're going to try to actually calibrate to each one of these, so we're really trying to optimize our model because there are going to be errors in each of these terms, and so we want to optimize to get the best results. So our any water balance model is very simply evapotranspiration, precipitation, and snowmelt, sublimation, runoff. But one of the things that we learned is that in many of the systems, fractured rock underlies very porous soil. And in order to get water to flow into the fractures, to get recharge, you need to saturate at the soil-bedrock interface. And to do that, you need to overcome the soil storage capacity, which is just a field capacity. Once you get above field capacity, water drains down, it can saturate. We have field data that show this happens. We show when it happens. We have ongoing experiments in the field where we're monitoring this. But in the end, when we get this fracture flow to go on, or even some in more porous rock, we can get infiltration down below the root zone and get at eventually recharge, which may take tens of years, years to hundreds of years in some cases. So this is our water balance that we have conceptualized based on field experiments and field measurements going over tens of years. To take this into a transient regional modeling scale, we have to take a model that uses this conceptualized model. We use geospatial data sets. The digital elevation model is the basis, then the geology, because we need to know what the permeability of the underlying bedrock is, what the soils data tell us about field capacity and wilting point, what potential evapotranspiration is, air temperature and precipitation that we get in spatial data sets. So this is our basic model. We have our energy balance run by a solar radiation model, which is an hourly model, takes into the impacts of cloudiness, topographic shading, slope and aspect, and precipitation and air temperature we get from the PRISM data set that comes out of Oregon State University. We have snow accumulation and melt using the National Weather Service Snow 17 model. And when we put all this together, we're going to come up with the amount of excess water. The excess water that we can't evaporate away, is going to be in the soil profile. And that's central to the water balance, is this field capacity, total porosity, wilting point, bedrock permeability. The water that's held, plant available water, is what goes into our actual evapotranspiration. The difference between potential ET and actual ET is our climatic water deficit. That's the water the plants would have used had it been available to them. And that's highly correlated to forest die-off, to forest fire intensity, to plant distributions on the landscape. So that's an important number that comes out of here, but it's dependent upon this actual evapotranspiration, which is dependent upon soil water holding capacity. What's left, what isn't evaporated, goes into either local recharge or local runoff. That's our water supply. That can either be basin discharge or groundwater recharge. Some of the local runoff becomes recharge. Some of the local recharge actually comes back out as base flow further down the system. But this is the general water balance model that we have put into a Fortran code that can calculate this on a monthly or daily time step for very large areas. So this is an example of a map. This is for California, of what the local runoff is, the runoff generated, where it's generated. We do this on a monthly basis. This is just a long-term, 30-year average. And then the distribution of recharge and what that number turns out to be. And we can do this, again, at a 270-meter scale. And even though we've done California, we have just finished the Great Basin. We have finished the upper and lower Colorado, or we're working on the upper and lower Colorado right now. And we have the potential to do Oregon, Washington, Idaho, and Montana as well. And so soils for those regions are what we're going to be working with next. So these are the kind of maps we can produce on a monthly basis or a daily basis to tell us about water supply, which is important for California right now, being in our 4th or 5th year of a drought. So when we talk about each component part, we'll look at each one and talk about solar radiation and then go through these different pieces of the model to show you how we get to the final value. So solar radiation, we calibrate against radiation stations across California. The example on the left is showing a station from, this is a California Irrigation Management Information System, or CEMA stations. They have them for Arizona and for Utah and Nevada. And this particular station was hard to model because it has about, well, it's higher than what it should be because apparently somebody changed the sensor and forgot to change the calibration equation in the data logger. The other stations in California are giving us the right amount of radiation that we typically get from clear sky radiation, and then we've added cloudy sky to this and showing the match for these different stations. We can map out the parameters we need to make cloudy sky radiation out of the difference between minimum and maximum air temperature. And that's how we come up with these radiation component in the model. Then it's distributed across the landscape. This is daily potential evapotranspiration. Even though that Camino station on the left-hand side of the screen was off, when we add the air temperature and other components, we can get a little bit better estimate of what the potential ET was. But we have to correct for some bad data. In some cases, the model is better than the measured data. But this is now our way of getting at daily or eventually monthly potential evapotranspiration. These are a series of stations there. The symbols are not quite right. They happens when you have ArcGIS on a computer that probably doesn't have ARC, just to show you the distribution of the stations and the detail of the potential evapotranspiration in north and south-facing slopes. In this case, you see Yosemite National Park highlighted below. But this is our study domain that we're working with right now. And these are some of the results of the monthly values over those stations and a one-to-one line that shows that we're doing a reasonably good job getting at monthly evapotranspiration in the desert Southwest. So that's our potential evapotranspiration. We go into the snow processes. We want to make sure we accumulate snow because in our measurements that we've developed, we've learned that particularly in the Great Basin, you have to accumulate 2 or 3 or 4 months of precipitation in a snowpack and then melt it out all at one time to get enough water to overcome the soil storage capacity to get at recharge. Most of the recharge in the Great Basin comes from winter precipitation as snowpack. If we transition into more rainfall, we're going to get less recharge and more runoff. But we have to go after the calibration of the snow system. We do that in 2 different ways. One is looking at snow-covered area, where MODIS data has snow-covered area, where we say there is snow-covered area, make sure that we have it where they have it and don't have it where they don't, and over the seasonality. So we use data from NASA, we use JPL data to try to make this mapped across the southwestern U.S. So that's one of the ways we look at snow. The other is we look at whether we can accumulate snow where there are glacier fields and that we can maintain the snow over the season, which we can do, so that we don't have areas of snow accumulation that last longer than what we see in the field. And then finally, we look at snow course data. These are snow courses that have been run all over the state of California. The months that you see in the graph on the left are just simply snow water equivalent in millimeters per month on the particular month that they did the snow survey. We have to change the parameters of the National Weather Service Snow 17 model in order to get a spatial distribution of what those parameters are. The parameters, for example, are the maximum melt and when the maximum melt can occur and how much you can melt in a given month. And then the snow accumulation temperature, what temperature do you have to have? In some cases we find, and we're not sure why it's that way, but we have to have 3 to 4 degrees we can accumulate snow in order to get the right amount of snow. So we do this for these 87 snow courses across the Sierra Nevada mountain. We look at our correlation coefficient, or R-squareds, for these, and we can develop a map of the distribution and what the parameters have to be, and then we can make a map of temperature and snow accumulation temperature, and the melt time, and distribute our snow over the season. So this is an important part of getting at the snow term and doing very specific calibrations on snow, and we're working on that in the Great Basin and Upper Lower Colorado as well. So when we get the outflow from our model, we have several subsurface basins that we want to look at. The top, this is Hopland. This is in the Russian River area in Sonoma County, in coastal California. We have our Basin Characterization Model, recharge and runoff, and those go into 3 zones, groundwater reservoirs. You can see that on the lower right-hand side. We have a surface reservoir, a shallow reservoir, and a deep reservoir. This water can either come back up or go into the alluvial valleys further downstream. We have reservoir losses, agricultural losses, and diversions across the landscape that we have to account for in order to get what we call impaired flows that come out, in this case, in Hopland. So we can do a pretty good job getting at the runoff term from this model on a monthly time step or a daily time step. But all of these component parts are post-processed from the model output so that we can come up with any pour point that we define in the landscape. We can come up with how much recharge and runoff is going to be in that basin. So this is part of our calibration process as well. We try to make sure we get the timing right. This is the timing of runoff, so we can get runoff when runoff is occurring. The graphs on the right are just 2 stations showing that we get runoff when there's snow melt, when they say there is snow melt. We don't want to have a delay in the system. You don't want the total annual amount to be right without having the monthly amounts at the right time. So we're just showing that we can accomplish that with this particular model. So now we get into the water balance and actual evapotranspiration, and where we're working with the soils data and where we've had to make some changes in the assumptions that we use, and where we're looking for some feedback and some help on understanding this, our soils data and the data that you guys are generating, and we desperately need to get it right. So in general, SSURGO has field capacity at 0.03 megapascals or third bar, and wilting point at 1.5 bars or 1.5 megapascals. And plant available water is something between that. That's where we started this work. We just took the field capacity and wilting point data from the SSURGO data set. Well, originally we started with StatsGo, and where StatsGo exists and SSURGO does not, we still use the StatsGo data set. But we, like the SSURGO data set, we get much finer resolution with the SSURGO data set. But when we use that particular data set and the third bar and 1.5 bars, you have to remember I went to school back in the 80s when we didn't use megapascals, we used bars. This is the kind of results we get for recharge. This is work in the Great Basin, just to show that we were overestimating recharge. And the scale below is logarithmic and the one above is linear. And the reason that we are higher in estimating recharge is that we could not evaporate enough water from the soils. And we had too much excess water that went into recharge. And that's the alluvial valleys using 2.01 meters soil depth, which I believe is the limit of the SSURGO data set in terms of its soil depth. But we know that the rooting depth is much deeper than that. And so we have to consider non-soil rooting depth and water holding capacities as well. But we'll show what we did on trying to solve this particular problem. One of the things that we did learn, because we had a pretty good drought in California and are still having one, this is a graph of total soil water storage. We have 4 TDR probes from the surface to bedrock. We have 4 heat dissipation probes to measure water potential or matrix potential. And then we add these up to come up with a water content. The red is the total water storage that we measured in the field. The green is the model that we have, and one of the things we discovered is that in normal years, plant water use goes to about 15 to 30 bars, and that's the dashed line. But you can see that the soil water content went below wilting point. It went, in fact, in many cases, they got to about 100 or 200 bars because it was becoming air dry in the surface, and that we were able to, the atmosphere was extracting water from the soil where the plants had to stop. And we had to change our model to simulate the idea of drying out because of atmospheric drying of the system. And once we incorporated that, then we could start to match the real soils data. So another component part is how dry can a soil be from atmospheric evaporation, and how deep can it go? And in this case, we saw it down to a meter. We were getting water potentials up to 100 bars, and the surface was about 1,000 bars. And we could do that with our very well calibrated heat dissipation probes. So this was an important part of our modeling too, to learn that these soils can dry out through atmospheric processes as well as plant processes. So we changed, in work that I did when I was a graduate student at Oregon State, is going out measuring field capacity in the wintertime in all the soils that I could find in southern Oregon. I think I had about 40 different soil types. And we found that the field capacity for these wildland soils was around 1/10 of a bar or wetter in many cases. So we wanted to change it to a different water potential, and field capacity or wilting point could be at 30 bars, or blue oaks can pull water out to about 40 or 50 bars, creosote around 60 bars, and so we wanted to come up with a different way to estimate water holding capacity. So we decided to use texture and recalculate our own water potential and water content at that potential. There was a series of literature review that we did. Galen Campbell had his Soil Physics with Basic book. Goulden and Larson did some water retention for particle size distributions in organic matter. Rawls and others did the effect of organic matter. And then Saxton and Rawls had water characteristics by texture and organic matter. So we looked at all of these. We tried them all out. They were in general agreement, although the Saxton and Rawls had a much more sensitive organic matter to water holding capacity, and we have a program in California trying to look at changing organic matter in rangeland soils to sequester carbon, increase water holding capacity, and increase forage quality. That's a funded project, so we're going to be working all over California trying to look at soil organic matter, and we wanted to use this equation. So we developed this particular one to come up with a whole series of water potentials, and then we'll use our vegetation mapping to tell us how dry can the atmosphere, or can the plants pull. If it's an oak woodland or a pine forest or a grassland, we'll have different potentials. So we're using this kind of information to come up with new maps. And this is an example of some SSURGO hydraulic properties. This is the Upper Colorado where we're working now and just developing these. So this is soil water storage capacity. So the SSURGO data gives us some fairly fine detail, which we are really pleased to have for this data set. Here's an example using the SSURGO properties from the hydrologic properties we get from SSURGO, or if we use texture, we can get a change in the water holding capacity. You see up in the northern part of the area in around Mount Shasta, we get a much higher water holding capacity if we use the textural data than if we just use the basic SSURGO data alone. So now we have this map, water holding capacity. We get an idea how much we can store in the soil. And this is going to help us out, and I'll show you that in just a second here. This is a close-up to show you that area that I was pointing to. This is Mount Shasta. There's a lot of volcanic ash around here, which seems to have an increased water holding capacity when we use texture. But this is just an example of the difference between the two data sets and why, and I'll show you why we end up using the one data set, which helps us out, which is this textural basis using a much wider range in water potential. So we're going to talk about the testing recharge results and getting at how we came about comparing these results against basin recharge. So chloride mass balance is one way to estimate recharge in a basin. The USGS uses mod flow models trying to match withdrawals, water level data from wells, and any other information we can to get at an estimate of the basin recharge. We have the Death Valley Regional Flow System. There's a Lower Walker Valley or Tooele Valley or the Utah Valley. Those are ones that we have pretty good confidence in. We also have discharge measurements, and then in California we have mod flow models as well that we're working with right now. So we're going to use these estimates of recharge to try to test out how well and what we need to do to change the soil properties so we can better match the recharge numbers. This is showing where recharge occurs in different basins in the Great Basin. current work that we've been doing and coming up with some numbers for what we think the recharge rates are in all of these basins. This is the result I showed earlier using the 2.01 meter soil depth and the SSURGO hydrologic properties and how we were doing against these reasonable estimates we thought we had of recharge. If we add the 4 meter soil depth and the SSURGO textural hydraulic properties, you can see the log scale below. We do a pretty good job, a much better job at fitting these estimates of recharge. So this is one of the ways we change the soil properties. Our geologic friends tell us that if it's mapped as quaternary alluvium, that means it was deep enough so that they couldn't see what the geology underneath it was, and so we needed to have at least a couple more meters of soil. So we used that and some geomorphology to try to get at what the actual characteristic soil depth was for plants to use. So now we have a way to get at recharge, but we had to change the soil properties to do a better job. Now, some of our ongoing model development is looking at estimates of actual evapotranspiration so we can incorporate vegetation specifically and seasonality. And this helps to concern another component of the water balance. This is an example of actual evapotranspiration calculated from NDVI and flux towers. These are 60-meter towers that were done by Goulden and Bales there at UC Merced. And this is their estimate, and they have several years of estimates of what the potential or the actual evapotranspiration is, which is dependent upon how much water you can hold in your soils. When we use the basic SSURGO hydrologic properties, we got the estimate up from the graph on the upper right. When we added the textural properties, we got the one on the lower left, which is a much closer fit to what the Goulden and Bales paper was. So we're starting to see we can make greater improvements by changing some of these properties to go after actual evapotranspiration as a way to add to the modeling. There are other estimates of actual ET by other organizations. Meredith Reitz at the USGS, she's a postdoc, and she's looking at annual estimates of evapotranspiration. She has about 12 years that she's done on an annual basis. You can see the Great Central Valley of California has a large amount because of the irrigated agriculture. There was another group, Formation Environmental, that did a project for the state of California, the Department of Water Resources, and they came up with monthly estimates of basin-wide actual evapotranspiration. They've divided California up into 278 basins in order to estimate what the monthly values were. They have both agriculture and non-agricultural estimates of actual ET based on their understanding of water movement in the valley. So we're going to use this data. I'm going to take these 278 basins and I'm going to break them up for this data set annual that Meredith Reitz did, because she has 1 kilometer cells where the Merced River is just one cell in itself in this particular model. So this is my method of evapotranspiration on the y-axis in acre feet on an annual basis. I believe this is for 2010. And this is using the 3rd bar and the 15 bar water potential that some of the lower estimates of ET basins seem to be okay, but as we get to the bigger and bigger basins, we're off because we're using the 3rd and 15 bar. We're not holding enough water in the soil to evaporate. If we go to the 10th bar and the 60 bar number, then we're holding enough water in the soil. We can either change the soil depth or we could change the water potential, and it seemed water potential made more sense because in order to match some of the recharge, I found I had to add 6 meters of soil in order to get enough water. Or if I just simply changed it to 60 bars and 10th bar, I could get enough. So this is an example of how we improved the model by changing what the water potentials were at field capacity and wilting point. Now, another term that we wanted to do was looking at seasonality. And in terms of seasonality, we were looking at the old agricultural K factor, that is a multiplier times PET. As we understand it, if you had, in our case, in the Bay Delta, our grasslands, although they're well-watered surfaces, have a K factor of about 0.8, which means they can only evaporate 80% of potential ET. If I use a K factor of 1, I get way more ET in the wintertime, this is January, and our plant physiology folks tell us that in, conifers, for instance, have antifreeze in their leaves or something like antifreeze, so they don't evaporate as much in the wintertime. They don't evaporate to potential. So if I change the K factor for each of these basins, and I realize it's assuming that all the vegetation is the same in the whole basin, by looking at the ratio of what I get as a K factor of 1 to what the actual ET was based on the DWR's estimate, then I can get a number and match exactly by saying that in January in this basin, in each of the basins, I have a K factor that might be something like 0.5 or 0.4 for that particular basin. And then the next month it might be 0.5, and the month after that, and so it goes through the whole season, and I can make this line almost a one-to-one line for each of the basins or for each of the months in California. In this case, I worked in 2011. There are some basins that have actual ET that are higher than what I have, and we've not resolved exactly why that is, and it may be that they're getting some agricultural or some return flows that they need to deal with. But in general, by changing the K factor, this is K factor less than 1 now, I can do a pretty good job matching. So I'm going after seasonality with this particular process. And then finally, we're looking at California having a whole series of mod flow models that have been done. The one that I showed you earlier that we matched by changing the soil properties was this number 5. That's the Death Valley Regional Flow Model. There are, about 15 basins in there, that sub-basins that we had to calibrate to each sub-basin. So we find that by having this monthly evapotranspiration, we get more realistic seasonality. We can represent disturbance. The other thing we want to do, if we come in with vegetation-specific ET, then if we have a fire like the rim fire, which burned thousands of acres, we can take the ET down to 0 for the first year. We're going to get more runoff, which is the only way we could actually match the stream flow we got after the burn event. But now we'll do a better job with better soil properties. We have modeled soil water content measurements at many locations, some NRCS, some universities, some are our own. And then we do these comparisons to these other mod flow models as a way to get at what recharge is and how we can calibrate the recharge. But to get recharge right, we have to get the ET right, we have to have the soil storage capacity right, we have to get the bedrock permeability and all of these component parts, because we don't want to have the recharge just being the error term. We want to get at it directly. So in summary, the BCM was developed on the basis of fundamental processes, observations, and physics. Fortunately for us, we worked on the Yucca Mountain project, and the federal government actually paid billions of dollars to do the studies on that. So we got hundreds and hundreds of thousands of dollars for 10 years to do whatever we needed to do to find out whether it was suitable or not. So we learned a lot about subsurface processes and soil controls over recharge and infiltration. So we calibrate the various component parts to improve the estimates of the water balance and recharge. We found that the mapped soil properties that we originally were using were not representing the rooting zone. They were underestimating actual ET, and so we overestimated recharge. But when we combine the remote sensing and the field measurements, we can develop actual rooting depths or soil water storage, and that was a big help. And then increasing the soil water holding capacity improved the estimates of actual ET and recharge, and that was a critical discovery of ours that we had to change those. And that once that happened, everything kind of came into sync. We could start to match ET, we could match recharge, and so we were glad to have discovered that. And that's sort of the end of what we're doing, but that's, you can see, I think, how clearly the soils information is critical to making this. And now we're moving into Utah, Colorado, Arizona, New Mexico, and we're going to be working on the soils there next.
So I'd like to add a couple of comments. This is a work in progress, and we've leveraged a handful of different projects to make sure that we're getting all the different components of the water balance correct. One of the things we're doing to impose seasonality is we've got Jim Thorne from UC Davis. He's a very well-known research ecologist who's worked with vegetation throughout California in a lot of detail, and we've got him helping us to parameterize our model for actual species-specific monthly evapotranspiration. So we'll be doing that, applying that to the model, and doing a better job of matching those ET records. Our ultimate goal is to be able to have all components of the water balance correct, and as you can see, when you look at our schematic of the model, the water balance calculation is very highly dependent on accuracy in the soil properties, and we have gone out to refine these soil properties using a handful of different approaches, and we would love to have feedback on if this seems to be a reasonable approach, if there are other research efforts that could be done in terms of collecting soil measurements in the field or estimating soil properties that could be done on a very large scale. Obviously, we don't just do one county or anything like that. We're doing the whole western U.S. at this point. So,
yeah, and one of the problems we run into is that we will look at the maps from SSURGO. We'll find we can get bulk density and porosity and organic matter, but no sand, silt, or clay estimates. And so we have gaps in these data sets, so we're not sure quite why we have the gaps or how we would fill the gaps. We've made some estimates, but that's the thing we're running into at some locations. As you know, SSURGO is not everywhere, and StatsGO is not perfect. So those are some of the things we're trying to resolve. Now, I see there were a couple of questions here. One was, what elements are we using from SSURGO? We're using the depth, we're using the porosity, we're using the organic matter. We were using field capacity and wilting point. Now we're going to sand, silt, and clay to try to get at the wilting point and field capacity. And I think I explained how we got the crop coefficients. And then there's another question that, how are the hydrologic properties determined from SSURGO texture, adjusted for rock fragments? No, we haven't done that yet. Actually, if you look at, let me see here. It's, if I find it. There's actually a Soil Science Society publication number 13 called Erosion and Productivity of Soil Containing Rock Fragments, and I actually wrote one of the chapters that was called Physical Properties of Rock Fragments and Their Effect on Available Water and Skeletal Soil. So I'm just making the point that I actually am aware of it, and that even though I wrote the chapter, I'm not actually applying it just yet. Okay, so the 15 bar and third bar water content values are on a whole soil basis and account for rock fragment volume. That may be why I came up with slightly different numbers. I went backwards and I looked at what the textural class was, and then I calculated based on the third bar and 15 bars, what would the water content be? And I came up with numbers that said on a just textural basis without rock fragments, it was something like a half a bar water potential would have been the effective water content. So the rock fragments obviously were having an impact on it. And I suppose I should try to make that calculation.
So we're also doing a weighted average of the different layers.
We do a weighted average of the different layers, but one of the things is we're trying to match actual ET, and there are two ways we can do that. One is we can change the water potentials to get a water holding capacity, or we can change the depth, because we don't really know what depth the roots are pulling water from. And so we could do it any one of two ways, and we're not sure which way we should go. We try to be as realistic as we can, saying that, well, the depth is probably not much, maybe 30% different than what you have. But we know that when we're in some soils, we know the roots are pulling out of the fractured rock or out of the weathered rock. So I think that would answer that question. What were the other?
So we'll give people a moment to compose their thoughts and enter a question. I don't know if there's a question from here in the room with me. Alan, one of the ideas that kind of comes to mind is, when we describe a soil, and if it's on a slope, we don't necessarily do it perpendicular to the soil surface. So if the soil's on a slope, we'll sort of go straight down as like as a plumb bob.
Right.
You can say it that way. And I don't know if that difference means anything in a model. You know, you've got a different angle, so it kind of changes the depth of the different layers. Do you understand that concept I'm trying to get at?
I understand the concept, yeah.
So one of the uncertainties on sloping surfaces with relatively shallow soils is that the plants often are extracting water from the fractured or fractured bedrock, and so we have a component in our model that is a depth of bedrock that the soils can actually investigate to try to get a little bit of that realistically into the picture. You know, whether or not it's a tenth of a meter or 2/10 of a meter or whatever, at that point you're talking about a lot of water, so sometimes you have to be able to extract it from something other than the soil.
Any other questions out there? Yep, go ahead.
I just want to say this is a fascinating presentation. One question I have is if you're using the SSURGO data, if you've actually taken data from the characterization data where there are measured values for, well, depending on the soil, sandy soils 1/10 bar and 1,500 kilopascals. But for other soils, it would be the 1/3 bar to 15 bar, and use those actual measured numbers and apply those to the soil series and see if there's a difference between what's being estimated versus an actual measurement.
Yeah, we have not done that, and one of the reasons is that it's a huge area, and it would probably take us most of our time just to do that alone. And we try to optimize our time between the different component parts. And if we get to these critical soil areas where we're getting really specific data, that's probably something we should do. We're working right now to develop a statewide soil moisture monitoring program. And so we've been pulling up all of the records of all of the data, or all of the station data that exists, TDR for water content, and likely we should go to each of the soil types that's in and look at that specific data to better understand the data from the field measurements.
I'd like to ask a question back. So there are field measurements made in the field from samples taken in soil tips. How are those measurements extrapolated across the surface for a polygon that we then use when we get our water content at field pass here, wilting point?
Well, they're put in basically the SSURGO data is class data, is how I would answer it. So we take specific measurements, but then we group them into classes with aggregated, yeah. So it's not actually necessarily a statistical value. And then we put in our data set, we'll put in a low, a high, and then a representative value, which may or may not be the midpoint.
Right. So the soil scientists from that area would look at some measured data and plug those numbers in there, but it would represent a class for whatever that named soil was in that map unit. So it's
okay. Okay, I see a couple questions here. I'm going to read them. Did I understand correctly that you have data that shows atmospheric conditions, i.e. humidity, can suck moisture out of the soil up to a meter? Yes. We were fortunate enough, we put in, and there was another question about where the TDR probes installed horizontal or vertical or at different depths. And I'm going to answer both of those questions. We used TDR at 4 different depths using a geometric progression down to bedrock, and we had heat dissipation probes to measure water potential. and they were put in horizontally and co-located with the heat dissipation probes so that we could get at that. And yes, we did see from our water potential measurements, because of the drought was so severe in 2014, we could actually see a really good drying down to a meter deep where the water potentials were over 100 bars, yet the vegetation had to stop at the at about 30 bars, but the atmosphere could manage to continually take the moisture out. There's another question here. It says, what is the source of geologic data you're using? Just bedrock type or superficial deposit? Is the geomapping complete for the region? Laura, you want to answer that?
We use whatever we can get, and so there are some places where there's geomorphic mapping that has informed local geologic maps. We're fortunate to have a lot of that happening in some of the Mojave Desert. For California, for example, we're using the 1 to 750,000 geologic map. And the key is that we are making estimates of shallow bedrock permeability to allow us to spatially distribute recharge differently across the region. So we don't obviously have maps of bedrock permeability, but we've worked with a number of geologists to get expert opinion on how different geologic types in a given location how they are different in the shallow subsurface. I'm not talking about deep fractures. We're talking about how water actually gets into the bedrock. And so we'll get tables from somebody who says this bedrock in this location is more permeable than this, a lot more permeable than this, or similar or less or whatever. So then we can start with a beginning point and use that to calibrate to Streamflow. And in our post-processing, we can have too much or too little recharge to be able to match the hydrographs and the base flow, and then we can tweak the numbers a little bit. And we've done this at locations across the entire desert Southwest.
So we do actually now have maps of what we think our best estimate of what the bedrock permeability is in the near surface. We have done some experiments where we'll use our TDR probes and we'll watch the soil actually wet up, be fully saturated, and during snowmelt, and then a freeze will come along for the next 2 or 3 days, and we'll watch that water drain out of the system. And these are flat systems, and so we can watch it drain out at about, in this particular one that we saw was about 12 millimeters a day, is what the drainage was from the saturated system.
Into fractured granite.
Into fractured granites. So that gave us an estimate of what the permeability was, and we've had that in a couple other locations. So that's one of the ways we try to get at it. We wish we had more, but
all right, well, it looks like that's exhausted our questions. I want to thank Lorraine and Alan for your time and effort to make this presentation today, and thanks to all the participants for joining in. We had more than 70 people join today's webinar. The on-demand recording of this webinar will be available on our center's YouTube channel within a few days. So please feel free to let your colleagues know about this training opportunity. And this concludes our webinar presentation.
Thank you all.